If your engineering manager walked into your workspace right now and asked you to justify the value of your QA process in 3 minutes or less, what would you say? Most QA engineers reach for the number they know best: how many bugs were found this sprint? And that number, on its own, is almost completely meaningless to a business decision maker. Here is why. A high bug count could mean your testing is thorough and effective. It could also mean your development process is chaotic and the code quality is poor. You cannot tell which one it is from the number alone. Leadership does not care how many bugs you found. They care about risk specifically. What is the likelihood that something will go wrong in production and what will the impact be? They care about cost, how much time and money is quality work saving versus how much it is consuming? And they care about delivery predictability. Can the team ship reliably and with confidence, or is quality uncertainty causing delays and surprises? QA metrics are one of the most misunderstood areas of the entire profession. Teams track what is easy to measure instead of what actually drives better decisions. In this episode, we are going to identify the 5 metrics that every QA lead should be tracking, explain exactly how to calculate each one, show you how to present them to leadership in a way that builds credibility, and give you a framework for using them to make better quality decisions on your own team. By the end, you will have a metrics approach you can start implementing in your very next sprint. The first metric, and the one most teams are already tracking but often misusing, is defect density. Defect density measures the number of bugs found per unit of work. The unit you use can vary. It might be per feature, per story point, per sprint, per 1,000 lines of code, or per module of the application. The specific unit matters less than using it consistently over time so that you can see trends. On its own, a high defect density number sounds alarming. But context changes everything about what that number means. If your team just launched a complex new integration with a third-party payment processor and defect density spiked for that sprint, that is not necessarily surprising or concerning. Complex new work has more bugs. What is more informative is trend data. If your defect density has been rising steadily across 3 consecutive sprints and across multiple feature areas that are not new or unusually complex, that is a signal worth investigating. It might indicate that code quality standards are slipping, that testing time is consistently insufficient, that a particular area of the code base has accumulated significant technical debt, or that developers are under deadline pressure that is causing them to cut corners. The useful version of defect density is not a raw number. It is a trend line with context attached. When you present defect density to leadership, you are not just reporting the number. You are telling a story. Our defect density increased by 30% this sprint. The majority of defects were in the search and filtering functionality, and this correlates with the decision 3 weeks ago to reduce testing time on that feature due to timeline pressure. Here is my recommendation for addressing it. That is a business narrative. That is what drives decisions. The second metric is escaped defect rate, and this is the one that gets leadership's attention fastest because it has a direct and visible cost. Escape defect rate measures the percentage of bugs that reach production, meaning real users encounter them, versus the total bugs found across both testing and production. The formula is straightforward: take the number of bugs discovered in production by users or monitoring tools, divide it by the total number of bugs found in that period including testing, and express the result as a percentage. A team that is catching 95% of their defects before production is performing very differently from a team catching 70%, even if the raw defect counts are similar. The reason this metric matters so much is the cost multiplier. A bug found during development or testing costs engineer time to fix and QA time to retest. A bug found by a customer costs all of that plus potential revenue loss from abandoned transactions, plus support costs to handle customer complaints, plus potential damage to the brand's reputation, plus the risk of losing users permanently. Research in the industry consistently shows that defects caught in production cost anywhere from 4 to 15 times more to resolve than defects caught during testing. When you can present that cost story alongside your escape defect rate data, the argument for investing in better test coverage or more testing time becomes compelling in purely financial terms. Tracking this metric over time and showing a downward trend, we went from 12% escape defects last quarter to 4% this quarter after implementing regression automation, gives leadership a concrete return on investment story for QA work. The third and fourth metrics are test coverage and test execution time, and they work together to tell a story about the sustainability and reliability of your testing process. Test coverage can be measured in 2 distinct ways. The first is code coverage at the unit test level, measured by tools that instrument your code and track which lines, branches, and paths are exercised by your automated tests. A code coverage percentage below 60 on critical paths should be a documented and communicated risk. The second way to measure coverage is at the feature and requirement level, mapping your manual and automated test cases to your product requirements or user stories and identifying gaps. This gives you a business language view of coverage that is easier to communicate to product stakeholders than a code percentage. Both approaches have value and ideally you use both. Test execution time matters because slow tests get skipped. This is one of the most consistent patterns in QA across organizations of all sizes. If your regression test suite takes 4 hours to run, it will not be run on every pull request. It will not be run on every build. It will become something the team runs only before major releases, which means it stops providing the continuous quality signal it was designed to provide. Tracking execution time and setting targets. A reasonable goal for most teams is under 30 minutes for the critical path. Automated suite keeps your test investment practical and actually useful. When a release decision is being made and a stakeholder asks what was tested and how thoroughly, these two metrics, coverage percentage and execution time, give you a concrete and credible answer. The fifth metric, and one that is particularly useful for diagnosing process bottlenecks, is the combination of time to detect and time to resolve. Time to detect measures how quickly your team finds defects after the code that introduces them is written. A short time to detect indicates that your testing is tightly integrated with development. You are testing features as they are built rather than in a big batch at the end of the cycle. This is one of the key benefits of shift-left testing practices. A long time to detect means defects are sitting in the codebase for days or weeks before they are found, which increases the cost of fixing them because the developer has to context switch back to code they wrote long ago and other work may have built on top of the defective code. Time to resolve measures how long it takes from when a defect is logged to when it is fixed, retested, and closed. Together, these two metrics create a map of your team's quality process efficiency. If time to detect is short but time to resolve is consistently long, the bottleneck is in the fix and retest cycle. Developers may be overloaded, the defect prioritization process may be unclear, or there may be insufficient capacity for unplanned bug work during sprints. If time to detect is long, your testing process is happening too late in the development cycle and a shift-left approach would help. Both of these metrics are actionable in a way that raw defect counts simply are not. They point directly and specifically to where the process needs to change, and they give you the data to have that conversation with engineering leadership. Here is your action item from this episode. Take the 5 metrics we covered: defect density, escaped defect rate, test coverage, test execution time, and time to detect and resolve, and assess which ones you are currently measuring consistently. Pick the 2 that you are not tracking and set up a simple way to start collecting that data this sprint. You do not need a complex dashboard or specialized tooling on day 1. A spreadsheet with consistent data collected each sprint is enough to start. After 3 sprints, you will have trend data that is genuinely useful for quality conversations. And here is what changes when you have this data. Instead of walking into a leadership meeting and saying we need more time for testing, you walk in and say our escape defect rate has been above 10% for the last 2 sprints, which corresponds to 3 production incidents, and our analysis suggests we need 2 additional testing days per sprint to address the coverage gaps in our high-traffic user flows. That is a conversation that leadership can actually respond to. That is a conversation that results in real resource decisions. Subscribe to QA Career Lab for daily content. Next in this series, we are covering how to influence decisions and outcomes without formal authority, a skill every QA professional needs.